So yeah, this is about distance learning for relation extraction without labeled data. Presented by me, Toby Peoples. What was it? A relations extraction is a new approach. This is a new approach to extracting relational data from an unstructured text without the need of labeled data. This algorithm was created by all these people, Mike Mintz and so forth, at the Stanford University. And relation extraction, I guess the definition is the task of recognizing the assertion of a particular relationship between two or more entities in a text. For example, Kevin Shields was born in New York. One relation is to recognize the person, Kevin Shields, and the other relation would be to recognize the place of birth, so New York. Extracting relational facts, from unstructured text is a highly relevant topic and has many applications such as information retrieval, text summarization, question answering, and so forth. Previous approaches have typically relied on small data sets where many use little or no information. More recent approaches use deeper syntactic information. Similar is the method of Wu and Wild, which I think we had a presentation on a few weeks ago already. So it was like 3 weeks ago. Okay. So, there have been 3 previous learning paradigms: supervised approaches, purely unsupervised information extraction, and bootstrap learning. In supervised approaches, sentences in a corpus are first hand labeled for the presence of entities in the relationships between them. An automatic context system extraction is then performed to extract a wide variety of features such as lexical, syntactic, and semantic. And then supervised classifies and label the relations. Supervised approaches does have some disadvantages. Just labeling, it's a time-consuming, expensive, few relations, small corpus. Only works with a small corpus, it does not scale, and is domain-dependent. And the labeling is biased towards the text domain on a particular corpus. It's unsupervised approaches, which is extracting string of words between entities. It's very useful. It can be used for very large amounts of data, but the resulting relations are not easy to map, and the results can be questionable. And then bootstrapping is a very small seed instances or patterns. It's used for large corpus in an iterative fashion, but the resulting patterns often suffer from low precision and semantic drift, which semantic drift is the loss of relevance, such as a person was born in a particular city and a person may have lived in that same city. There may be a relation there, even though it's not relevant. It might be created by this algorithm. This new algorithm is based upon distance supervision, which combines the advantages of the previous approaches. And as stated before, it's an extension of the Snow-et-al paradigm. The algorithm is we primarily use a large semantic database called Freebase, which I'll get to later. Just before, some terminology. Relation refers to an ordered binary relation between entities, and relation instance refers to an individual ordered pairs. The example would be a person-nationality relation. Stephen Merritt, United States. Stephen Merritt, the person, United States, the country. And on to Freebase. Freebase is a large semantic database. It contains 116 million instances of relations and between 9 million entities. The data in Freebase is collected from a variety of sources, Wikipedia, and so forth. So basically, it's just a giant internet database, and users can create their own accounts and so forth, and add information and links to different databases to do a particular topic. It also contains the reverse of many of its relations, which are then merged when the so book, author, book. And here's an example of some of their relations. So, yeah. John Dugard, South Africa, is people, person, nationality, and then Belgium doing its location, location contains, and then the size of each relation is there. A few other things with Freebase is because the algorithm that we use is supervised by this database, rather than by label text, it does not suffer from problems such as overfitting and domain dependency that have been problems with the previous supervised systems. And supervising by a database also means that, unlike other approaches, the output uses canonical names for relations. Okay, and then the architecture. So we have the architecture consists of two steps. First is the training step, which in the training step all the entities identified in a sentence using a name entity tagger that labels persons, organizations, and locations. If a sentence contains two entities and those entities are in an instance of one of the Freebase relations, features would then be extracted from that sentence and added to a feature vector for the relation. The assumption with distance supervision is that if two entities participate in a relation, any sentence with those two entities may express that same relation. Due to the possibility of an incorrect queue, the algorithm trains. Actually, wait, that's next. So before I go on, the example of the training step. So we have here Footscray, is a suburb 5 kilometers west of Melbourne, Victoria. In Freebase, you'd have the entity there, location, Australian suburb, or location / city town. And from there you get training data, Footscray, Melbourne, and a label, so suburb, and feature X is AY. I would explain some of this. This is the testing step. Entities again identified using the named entity tagger, but this time every pair of entities in a sentence is considered a potential relation instance. An example would be if a pair of entities is in 10 sentences. In the test set, each sentence would have then have three features extracted from it, and the entity pair would then have 30 associated features. A regression classifier also predicts the relation name for each entity pair. And then here is another example of the testing step. Say here we have the location contains relation, so the Virginia Richmond and France Nantes. You have the sentence Richmond, the capital of Virginia, and another sentence Henry's etiquette of Nantes helped the Protestants of France. In this example here, some features such as the Richmond sentence would be very useful to that relation, and obviously the other features would not be so relevant. And one of the main advantages of the architecture is the ability to combine information from many mentions of the same relation. This works well with a film director example. So you have the Coen brothers directed the film Big Lebowski, and you might have Tim Bevan co-produced the cult film Big Lebowski, and then from then you'd have a relation between those two, which would produce evidence for the film director relation. Then onto features. There are five features, which are based on standard lexical and syntactic features from the literature. So you'd have lexical, syntactic, named entity tag, and feature conjunction. So with lexical features, describes a sequence of words between the two entities in the sentence which they appear, and the part of speech tags of these words. So there's a flag indicating which entity came first in the sentence, a window of K words to the left, entity 1, and their part of speech tags, and a window of K words to the right, entity 2, and part of their speech tags. So here's an example of features for astronomer Edmund Hubble, who was born in Marshfield, Missouri. So lexical features here and some syntactical features as well. So left window, the let's say that the entity 1 and middle, and then we have a right window, and then the other entity, the other NE2 here. Non-syntactic features. These features are obviously based on syntax, and each sentence is first parsed with the broad coverage dependency parser, minipar. A dependency parse consists of a set of words, Edward Hubble, and then chunks linked by directional dependencies, the pre, the pred, and the lex mod. For each sentence, a dependency path between the pair of entities is extracted. The dependency path consists of several a series of dependencies, directions, and word chunks, representing a traversal of the parse. So here's an example of that. You have sentence, and then the pre-med and the mod, and the peacock inside, and here is all synthetic. Okay, and then the syntactic features consist of the conjunction of a dependency path between two entities, and for each entity, one window node that is not part of the dependency path. A window node is a node connected to one of the two entities and not part of the dependency path. And finally, you have the name entity tag features. Every feature contains additionally a named entity tag for two entities. The tagger provides each word with a label from example person, location, organization, miscellaneous, so forth. And then here's an example at the end of the feature conjunction. Each feature consists of the conjunction of several attributes of the sentence, plus the named entity tags, plus two features, well, for the two features, sorry, to match all of the conjunctions. All of their conjunctions must match exactly. This yields low recall but high precision features. With small amounts of text, this would be quite problematic, but in these experiments, large amounts are used and allowing high precision features to work. For the experiments, as stated, for the unstructured text, the free-base Wikipedia extraction is used. The DUM consists of approximately 1.8 million articles with an average of 14.3 sentences per article, so roughly 6 billion words. For the experiments, half of these are used, 800,000 for training and 400,000 for testing. Wikipedia is also good because it's relatively up to date, and because its sentences tend to make explicit many facts that might be omitted in other omitted in Newswire. We have for the experiments, training and testing. For the entities are tested in two ways: with held out evaluation and with human evaluation. With the held out evaluation experiments, half of the instances of each relation that are not used in the training data are later used to compare against newly discovered instances that weren't in the free-base data. For human evaluation experiments, all 1.8 million relation instances are used in training. Only relation instances that do not appear in training data are extracted, so that means they're not already in free-base. And on to parsing and chunking. Each sentence of this unstructured text is this dependency parse by the minipar, produced a dependency graph. In pre-processing, consecutive words with the same entity tag are chunked. So here, Bradford and Cox becomes Bradford Cox, or Bradford / person Cox becomes. Chunking was just restricted as well to dependency parse of the sentence, i.e. no chunks across subtrees. That means basically chunks must be continuous in the parse. The system needs negative training data as well for the purpose of constructing the classifier. So a feature vector in the training phase is built for an unrelated relation by randomly selecting entity pairs that do not appear in any free-base relation and extracting features for them. A multi-class logistic classifier optimized using LBFGS GS with Gaussian regularization is also used. This takes as input an entity pair and a feature vector and returns the relation name and a confidence score based on the probability of the entity pair belonging to that relation. Afterwards, these can be ranked accordingly with the confidence score and used to generate the list of the n most likely n new relation instances. So we have here examples of the high weight features of separate relations. So the syntactic feature, the lexical feature, and it's then reversed, and we have the name entity tag, the two name entity tags of each entity. So it's film, country, and so forth. Okay. Evaluation. Labels are evaluated in two ways. Firstly, automatically, and secondly, manually. Automatically by holding out part of the freebase relation data during training and comparing newly discovered relation instances against this held out data. And of course manually by having humans who look at each pair positively, at each positively labeled entity pair. Both evaluations and then allow us to calculate the precision of the system for the best number of instances. With held-out evaluation, it does suffer from false negatives, but it does give a rough measure of precision without requiring expensive human evaluation, therefore making it useful for parameter settings. The combination of syntactic lexical features also offers a substantial improvement in precision over either of these feature sets on its own. And here's the performance of the classifier on the held-out freebase relation. So this is using both syntax, and here's using surface. So by combining these two, they have a slight improvement on the precision of the classifying of the relational data. And with the human evaluation, it's performed by Amazon's Mechanical Turk service. These experiments are run using syntactical features, once with lexical features, and once with both. And here's the estimated precision of the human evaluation experiments of the highest ranked 100 and 100 results per relation using stratified samples. Okay. Yeah, and then basic summary. In summary, the distance supervision extracts high precision patterns for a reasonably large number of relations. The combination of syntactic and lexical features provides a better performance than either feature set on its own, and syntactic features consistently outperform lexical features. Attention, questions?
Okay, thank you. Question.
Yeah.
What would happen if the text data contained a relation that was not already in freebase? What kind of result would this give to this relation?
Maybe if I read it was in somewhere. I think it was they would add it to their database. Because I think part of the point of using freebase, they look for relations that aren't in freebase as part of their testing, and then they add them to the feature vector, I think, was what I read. Yeah, I think so. I'm not 100% too sure actually. But did read it somewhere, but it's only mentioned briefly, but I can't remember where it was. So. So I don't know, I'm not sure, so.
More question. So if you go to slide 15,
Yeah.
I didn't get that.
Okay. I've got a so the first sentence here would provide evidence for film director relation,
Mm-hmm.
but it could also be evidence for film writer or film producer as well. And therefore, and the second sentence does not mention, well, actually does mention it's a film, but there could also be evidence for the relation to this film. I mean, in isolation, neither of these features is conclusive, but in combination, they are.
Mm.
Or maybe, like, it's the wrong example, but if it didn't say film, if it's co-produced The Big Lebowski, it wouldn't say film, but you could form a relation to the film from this other sentence. That's the point.
Okay. If you go to slide 21 again. So what is a window node? Would be astronomer in this example, or would be, for example.
No, I'm not so sure either. It wasn't explained either that clearly, but I think when it says in the example, it's.
Or if you go.
I think the window node would be astronomer Edward Hubble. That's on one side, and then the other side the other window node would be Marshall in Missouri.
Okay.
Yeah, because there's two window nodes to the left, so, and then the other one there will be the right window node. And then you'd have your pre-modern, pre-comp inside.
Because if you go to slide 28. Okay. Okay, so yeah, just want to look at it.
Okay,
Mm. Yeah, other question?
I'll try and find the answer.
Okay, in case there are no more questions, thank you again.